Today we're going to talk about light, also known as electromagnetic radiation. Now, you've probably heard since middle school that light is a form of electromagnetic radiation. What exactly does that mean? What is it about light that makes it similar to electric charges, to refrigerator magnets? How can we relate all of these three seemingly very different things? And to give some context for this, I think it's helpful to look at some historical experiments that people have done that illustrated the connection between light that we see, electricity, and magnetism. And I'm going to start by going back to 1800. There's this guy named Herschel, and he, at the time, is thinking, well, light has some energy to it, and we know that if we shine light through a prism, then we get the different colors of the spectrum, red, green, blue, etc. And let's try to see if we shine light through a prism, let's try to figure out how much energy each color has. So does red light get more energy than blue light? Does blue light get more than green light, etc.? So we start, this is 1800, so there's no light bulbs yet. And pretty much the only way to get a good amount of light is to use sunlight. So what he does is takes some sunlight and he shines it through a hole in the wall, so that you have a thin beam of light coming through hitting your prism. Here's your prism. And as we know, the prism is going to separate the light into its various constituent colors. So we have red, green, blue, purple. And as a control, he's also going to consider what happens in shade. So we look at each of these different rays of light that are coming out, each of the different colors that the prism is projecting beyond it. And next to that, he puts different thermometers. And the thought is that if you take a thermometer and put it in sunlight, the thermometer is going to heat up. You know, if you go outside and you stand in the sun for a long time, you start to get, in the sunlight for a while, you start to get hot. So he's going to measure the amount of temperature increase for each of these thermometers. And he's going to use that as a gauge for which wavelength of light, which different color has the most energy in it. Now, if you had to guess, which would you say? Is it going to be shade, red light, green light, blue light, or violet light? Well, somewhat shockingly, the biggest temperature increase was always shade. Shade had the biggest temperature increase. Now, how does that make any sense? Well, it turns out shade, or in this case, what we would consider to be the absence of visible light, is not an indication that there is no electromagnetic waves that are going there. Because if we look at this far end of the spectrum past the visible, it turns out that there is some light. Or I shouldn't say light, because light implies visible light. There is some electromagnetic radiation that's going past the red light into the visible. And since it's past the red light, we call this infrared, or IR for short. This was one of the first indications that there's a phenomena beyond what we can see with our eyes. There is electromagnetic radiation, a different type of light that extends beyond the visible range of the spectrum. So here's your visible range, red through purple. There's some electromagnetic radiation that extends beyond the visible. And this was only the first in a series of experiments that demonstrated that there was electromagnetic radiation beyond what we would normally see just with our eyes. So here I have a cathode ray tube, and when I bring a high voltage source next to the tube, you will see that will create a stream of electrons going across the tube. Now, I'm just going to turn off my lights here for a sec. And when I bring my high voltage source close, you can see that stream of electrons. Now, we can tell that green beam of light is a stream of electrons because if I start my stream up again and I bring a magnet in from up top, you can see I can deflect that beam. Let's see if we can get that in focus. There we go. You can see I can deflect that beam because moving charges feel a force when they're in a magnetic field. Now, the green light that we're emitting is actually not the light that I want to talk about. Let me just turn my lights back on. That green light, when the electrons go across the cathode ray tube, is not the important one here because it turns out when the electrodes hit the opposite end of the cathode ray tube, they are going to emit a different type of electromagnetic radiation, one that is not inside the visible range. There was a scientist who was working with these cathode ray tubes. His name was Röntgen. This was around 1895. And what he discovered is that you take a high voltage source, just like we've done before, and you apply that to your cathode ray tube. Just as we saw previously, you get this green line of electrons that come floating across. The green line is not the radiation we're looking at. That's still in the visible spectrum. But what Röntgen discovered was that when the electrons collide with at the opposite end of the cathode ray tube, it emits some other type of radiation. And that other type of radiation, you can tell it's some other type of radiation because when it hits some target over here, it starts to glow. But the confusing part about this is that this electromagnetic radiation can pass through walls, which was kind of surprising. It went through walls and other types of material. It couldn't pass through lead, but for certain materials it could pass right through. Unlike the visible radiation that we see, the visible light radiation, this type of radiation, which was radiating from this point where the electrons were hitting the wall of the cathode ray tube, for whatever reason, it could penetrate through objects, which was a very strange thing. So it was this invisible, penetrating radiation. And this was very mysterious to the scientists at the time. How could something be invisible and yet we can still detect it? And not only that, it can pass through walls. So because it was so mysterious, they gave it the name X-rays. The last piece of the puzzle was put together by a guy named James Clerk Maxwell around 1873. And what Maxwell figured out, and had great intuition for, had to deal with what we know about electromagnetic induction. So we know that if I have a wire loop, here's my wire loop drawn in white, and I put a changing magnetic field through it. Suppose my magnetic field is increasing. We'll want to induce a magnetic field in the opposite direction. And to do that, we first induce an electromagnetic force in the opposite direction, and that will give us a current. A current that goes around like this. So, what does this tell us? Well, this tells us that a changing magnetic field, it's pushing charges around. So that must mean that the changing magnetic field creates a changing electric field, or creates an electric field, I should say. creates an E field. Changing magnetic field creates an electric field. What Maxwell had the great intuition to, his great intuition was essentially that what if the reverse is also true? So what if a changing electric field creates a magnetic field? A changing electric field creates a magnetic field. That was Maxwell's big intuitional leap. So Maxwell has this intuition for how electric and magnetic fields might interact with each other. And he did what any good physicist would do. He didn't just say, oh, well, this must be true. He worked out the math and tried to show what the consequences of this would be. He came up with some mathematics that relied on a series of equations. So the equations were basically what we know about Coulomb's law and how electric fields are created, what we know about Ampere's law and how magnetic fields are created, and what we know about induction from Faraday's law. So how changing magnetic fields can create a changing electric field. And he threw in some extra terms in there to show that a changing electric field could also create a magnetic field. And he worked out what would happen if that were the case. And the end result, which we're not going to derive because it involves some calculus, in fact, just these equations alone involve some calculus, but he came up with these equations, which are known as wave equations. These are the differential equation form of a wave equation. And the end result of this is that you get this constant, known as the wave speed. Now, the wave speed, again, it's just some constant that we call c. But if you derive this with your electric and magnetic equations, the reasons we know it's a constant is because it just depends on the electric and magnetic constants. It depends on the permittivity of free space for electrostatics, and the permeability of free space for magnetostatics, for magnetism. And this wave speed, according to Maxwell's math, should just be 1 over the square root of the magnetic constant times the electric constant. And if you multiply that out, you get a wave speed of 3 times 10 to the 8 meters per second. Now, Maxwell didn't do any experiments here. He just said, all right, I have this idea for the way I think it should be. I have some evidence that shows that this is how electricity works, this is how magnetism works, this is how induction works. Let's see if I apply my intuition to what we already know to be true. Let's figure out what the results of that would be. And he got these 2 wave equations, which are coupled to each other, so that the electric and magnetic fields would go back and forth creating. So if I create a changing electric field, that creates a changing magnetic field. And then the changing magnetic field creates a changing electric field, which creates a changing... It goes on and on. It's the song that never ends. Forever and ever, which would give you the idea that if you do have this idea that changing electric fields create magnetic fields, that you'd have this self-propagating wave that would go on forever and ever, which is basically what we know light to be. Right? Or at least we know at the time they knew it was some sort of wave that propagated forever and ever. The trick is, like any good scientist, we know that if Maxwell's right, then the wave speed better be correct. And if we measure that wave speed, we better get 3 times 10 to the 8 meters per second. Now, we'll talk about how to measure that in just a second, but it is somewhat curious that these two, the wave speed is just a constant. Now, that doesn't seem like it should be that mysterious at first glance. You know, you're in your car, you turn your headlights on, the light goes out at that speed. But what if you're in your car and you're driving? Suppose, I'm going to work with a more familiar number rather than this. Suppose Maxwell came up with the speed of light, and he said the speed of light is 50 miles an hour. Right, you turn your headlights on, the light leaves at 50 miles an hour. Well, what if you're driving at 50 miles an hour? Well, then, relative to you, maybe it leaves at 50 miles an hour. But the person who's watching you drive down the highway might see the light leaving at 100 miles an hour. since it's 50, those two 50 miles an hour added together. So something screwy is going on here, the fact that the speed of light is measured to be constants. This is going to disrupt all of modern physics, but at least for now, it gives us a good way to measure whether or not Maxwell's theory is correct. We'll leave why this screws up all of modern physics to Einstein to figure it out once we get into the 20th century. As luck would have it, Maxwell did not have to wait very long to figure out whether or not his theory was correct. Because 200 years before Maxwell even came up with his theory, Romero had this idea to measure the period of the satellites orbiting Jupiter, the moons going around Jupiter. And what he found was that every once in a while, sometimes, Jupiter's moon was a little bit ahead of where it should be. And if you take into account the fact that sometimes Jupiter's moon is further away from us than at other times of the year, which is going to be due to the fact that Jupiter's moon is going around Jupiter, and also the fact that the Earth and the moon, and the Earth and Jupiter are getting further and closer to each other at different times of the year. But if you take both of those things into account, you can get a good estimate for what the speed of light is. Now, Romero didn't have super great equipment at the time, so he couldn't do a very precise measurement. But the more and more times people took the measurement, the closer they got to the number that Maxwell had found, which is that the speed of light is about 3 times 10 to the 8 meters per second, 300 million meters per second. If Maxwell's theory is correct, that electromagnetic radiation forms light and other types of electromagnetic waves, then it should be possible to create electromagnetic waves using electromagnetic equipment. And that's what Hertz decided to do in the late 1800s. He got a high voltage source and then applied it across two terminal ends, and the voltage was high enough between these 2 points that you could actually get a spark that oscillated back and forth. So you have some oscillating spark going back and forth between these two. And what Hertz was smart enough to figure out is that if Maxwell's theory is correct, there's got to be some electromagnetic wave that gets generated as a result of that spark, those electric charges, those electrons, jumping back and forth. And Hertz figured that there's got to be some electromagnetic wave that travels across. And what he knew is that if you put part of the metal wire, part of the metal loop here, so we've got a metal loop, but between the metal loop, we've got a gap right here, so that there's not quite enough, there's not quite a full conducting path here. But if we have an electromagnetic wave going across, we've got a wave in electric field. So here's our electric field lines, oscillating up and down as the wave travels toward our loop. And we have some magnetic field lines. Magnetic field. Well, as the electromagnetic radiation passes this loop, it's going to get a changing magnetic field passing through that. And we know a changing magnetic field passing through a loop of wire creates a changing magnetic flux, which induces an EMF, which induces a current across the circuit. So that there should be some sparks that jump across this gap. So that if I have my high voltage source creating sparks on one end of the room and my partial loop of wire on the other end of the room, I should be able to transmit energy through electromagnetic waves going across here. And in fact, that is what Hertz saw. And what he was observing was some of the first radio waves that people had ever created. final predictions of Maxwell's equations was that electromagnetic radiation could potentially have some polarization to it. What do I mean by that? Well, we've talked about the speed of light being a constant that we've called c. So let's suppose light is coming out of the board at you. So light's traveling to the camera, which it is right now. That's how we're measuring this picture that you're seeing. So the speed of light is coming out at the board. Well, it turns out that the electric field, which I will call E, has to be perpendicular to that velocity vector for the light. So if the light's coming out, E has to be perpendicular to that. So if light's going this way, I've got an electromagnetic field vector that's pointing up. If I turn to the side, you can see that's a right angle. Furthermore, it turns out that the magnetic field also has to be perpendicular to E, and it has to be perpendicular to C. So if I make my magnetic field point this way, then I will have a magnetic field that's perpendicular to E, and it's perpendicular to C. And the direction that the light is going to travel is actually determined by the right-hand rule. So what we do to figure out the direction that the light travels is we're going to take the electric field across through the magnetic field. So we take our right hand, point my fingers along the electric field, and I have to orient my hand in such a way that I can curl my fingers to the magnetic field. Then my thumb points in the direction of that the light is moving. So let's try that again. Let's have you guys play around with that. Suppose the magnetic field is pointing up like this, and your electric field, suppose your electric field is going into the board. So see if you can figure out which direction that's going to point. I'll give you a second. Pause the video. And unpause. Well, let's see. Electric field going into the board. I've got to point my fingers in such a way that I can orient them toward the magnetic field. So I've got to do this, E cross B, which means my thumb points this way. The light would have to be traveling to the right. Now that's, it's a fairly simple procedure. If you do it a few times, you can figure out how to figure out the direction the light is moving. But here's the end result. We've got an electric field that's pointing up over here, magnetic field pointing this way. Whatever's happening, we know that the changing electric field, so let's say my electric field is going down, creates a changing magnetic field. So the magnetic field would also be decreasing. So that what you get is going to look like this. Again, electric field, magnetic field over here. The light's doing this, with the magnetic field going into and out of phase with, sorry, not into and out of phase. Magnetic field going back and forth, just like the electric field does. This is your electromagnetic wave that's propagating through space. It's a coupled electric wave coupled with a magnetic wave. And because changing electric fields create changing magnetic fields, and changing magnetic fields create changing electric fields, it's this never-ending cycle that propagates forever and ever all the way throughout space.